All right, well, as you know, this is an unintended, was not expected, but what can I do? Um, the original plan, when I thought about what the second lecture would be, was actually completely different than what it turned out to be. So this is going to be a version, of course, of what we did in class yesterday. And the point is that I'm going to be talking about the sensitivity of the eigenvalue problem, all right? In other words, we all have some certain idea about eigenvalues and eigenvectors and so on. We've ran at them here and there. And in system identification, it's quite clear that we are going to be, at some point, identifying natural frequencies, mode shapes, damping ratios, and things like that. So we're identifying structures, right? Systems. Now, a lot of times what we're interested also is not only on the identification itself, but on the sensitivity of the identification to something changing. Because what we want to do is detect damage or detect a change or detect a flaw or something like that. So if we are focusing on, let's say, identified eigenvalues, we are interested somehow on what is the derivative, right? How fast is that eigenvalue going to change if a certain parameter changes, right? For example, how much will the first frequency change if the columns on the third level that are at this or that location suffer a change, a loss in stiffness? So in that context, it should be rather evident that we are interested in knowing something about the sensitivity problem, or how the eigenvalue, eigenvectors of a system vary with changes in the parameters that define the system. Okay, now the topic is actually rather large, and I am not going to pretend to cover the whole thing in every detail, for example, when it comes down to repeated eigenvalues and things like that. But we will cover right now in this lecture the core of it, all right? And for that, the other issue that arises is that there is quite a bit of background from linear algebra that creeps in. So I'm going to do my best to give you, the essential background from linear algebra that is needed before, just to make sure that things are clear. Some reference will have to be made again as by saying, well, remember that, and so on. So let's start with this, without any further introduction. What is the null space of a matrix? So we have a matrix Q, and we want to talk about the null space. Well, the first answer could be that there is none, right? There is no null space. But when is there a null space to the matrix Q? Well, there is a null space to the matrix Q if we can find a vector, let's say B, such that if we multiply the matrix times the vector, we get 0. Okay? Now, of course, I'm using here notation in the sense that Q is a matrix, B is a vector, and these numbers of zeros that I have here is also a vector, right? So you're going to grant me the fact that not always will I make these brackets and so on, but that it's understood that we're talking about Q being a matrix, B being a vector. Now, if it turns out that there is more than one B for which that is true, then we could say, for example, let's say that Q times B1 is 0, and so it's Q times B2 is 0, where B1 and B2 are not proportional to each other, obviously, right? Because if B2 was 2B1, that's obviously true. But B1 and B2 are linearly independent. So if that's the case, we would say that the null space of Q, right, in this case, would be made up of a subspace which has these two columns, B1 and B2. Now notice that these columns also, if B1 is in the null space and B2 is in the null space, so is any linear combination of B1 and B2, right? For example, B3 equals to alpha B1 plus beta B2 is obviously also in the null space, right? Since this would be Q times alpha B1 plus beta B2, which is equal to alpha times Q B1 plus beta times Q B2, and that is 0, since that is 0 and that is 0, right? Therefore, we have the Aeshelon null space. Now, today, in my discussion here on eigenvalue sensitivity, I'm not going to be talking about null spaces that are multiple. I'm going to be restricting the discussion to the case where the null space is a single vector. Okay? So, now we understand what we have for null space. Now, by the way, for a matrix to have a null space, it must be rank deficient, right? It must have some singular values that are 0. In fact, the number of 0 singular values is the size, is the dimension of the null space. Okay? Now, let's take a look briefly first, also as introduction to the eigenvalue problem. So here we have the eigenvalue problem, okay? Now, the eigenvalue problem would look like this. If I use Q as the matrix and phi as the eigenvector, we would say that the eigenvalue problem is like that, right? In other words, any vector phi j which when multiplied the matrix Q comes back, except for the scalar multiplication by lambda, we say that this is an eigenvector, right? And this is an eigenvalue. Now, to connect it with my previous discussion, I think it should be obvious to you that I can write this as Q minus the identity matrix times lambda j multiplied times the vector phi sub j is equal to 0, right? This equation is the same as this equation. And what it tells us in terms of the interpretation that we had before is what? That phi j is in the null space of the matrix Q minus I lambda j, right? That's very important for the discussion that's coming throughout, right? The eigenvector phi j is the null space of the matrix Q minus the identity lambda j, all right? And if you also want to think about it, you can say the eigenvalue lambda j is the number which is needed to reduce the rank of the matrix Q by 1. Because the rank of Q, if Q was a real matrix n by n, okay, and whose rank was n, full rank, then the rank of this is n minus 1, right? If phi j, if lambda j is a simple eigenvalue, non-repeated, and this is the eigenvector. So the eigenvalue lambda j reduces the rank of the matrix Q by 1, and the null space that gets created is the eigenvector. Okay? All right. Now, let's now with that sort of introductory note, begin. So let's take a look again. I'm going to change the notation from Q to A. I don't know why, but anyway, let's look the eigenvalue problem here like this. So I have A times lambda times phi j is phi j times lambda j. All right? Now, that is what we call, well, that's the eigenvalue problem for A. A question that comes to mind is, what does the eigenvalue problem look for A transpose? Well, I don't know if the eigenvectors are the same, so I will have to call this some other symbol. So I'll call it, let's say, C, right? But what I do know is that the eigenvalue is the same. Actually, I was using J, so let me just use J, right? Now, why do we know that transposition does not change the eigenvalues? Well, because the characteristic polynomial of a matrix is invariant with respect to transposition of the matrix. To illustrate that, in case that you are not completely clear on it, imagine that you have the matrix A, B, C, D, and you were interested in computing its eigenvalues, right? So you would take a look at the matrix A minus, well, okay, wait a minute. From this here, we also have that this is A minus I lambda J, right? Multiplied times phi j equal to 0. So what we have is the characteristic polynomial of this matrix that must be 0. So this matrix, if this is A, is equal to A minus lambda, D minus lambda, B, and C. And the characteristic polynomial is equal to A minus lambda multiplied times D minus lambda minus B times C, right? And so the root is lambda is whatever makes this polynomial equal to 0, right? Now, if we consider the transpose of the matrix, the operation that I did here, then AB would become the first column, CD would become the second column, and the characteristic polynomial of this matrix would be A minus lambda, D minus lambda, not the characteristic polynomial, A minus lambda I would be this would be C, this would be B, and we see that the characteristic polynomial would be A minus lambda times D minus lambda minus B times C, and that the eigenvalues would be whatever gives me 0, and you can see that these two characteristic polynomials are of course exactly the same, and that is true not only for a matrix that is 2 by 2, but for an arbitrary size. So, in summary, because the characteristic polynomial of a matrix is unchanged by the transposition of the matrix, the eigenvalues are unchanged by the transposition of the matrix. Okay? Now, once we accept that, then we are back to this point. Now, at this stage, we can say, let's take a look on this side, and let's take a transpose of this equation. So then we get C transpose times A is equal to C transpose times lambda J. There is no need to transpose lambda because that is a scalar, right? Now, from looking at these two equations, you can see why is it that we call the vectors phi the right side eigenvectors, because that means that when we multiply them on the right, they come back times a scalar. We call these vectors C the left side eigenvectors, in the sense that if we multiply them as a row on the left side of the matrix, the row that we get is exactly the same as the vector multiplied times the constant. Okay? So these are the right side eigenvectors, and these are the left side eigenvectors. Okay? Now, let's look at at clarifying the relationship between the right side and the left side eigenvectors. I could use J and K, but I'm going to use 1 and 2 for subscripts because it's easier not to make a mistake. And it's easy to see that 1 and 2 could be J and K. So if I look at the particular case 1, I would have this. And if I look over here at the particular case 2, we can write this. Okay? Now, if we if we pre-multiply this matrix, this side, times C2 transpose, then we would have this situation. Right? And if we post multiply this side by phi1, then we would have this situation, right? Now, if we call this equation 1 and this equation 2, you can see that equation 1 and equation 2 have exactly the same left side. Therefore, subtracting equation 2 from equation 1, we conclude that 0 is equal to phi2 transposed phi1, C2 transpose phi1 times lambda 2 minus lambda 1. Okay? And if we accept that we are dealing with a situation where the lambdas are different, that is, we're not dealing with repeated eigenvalues, that is, lambda 2 is not the same as lambda 1, or in this case, as I say, j and k, then we conclude that this must be identically equal to 0. And we could use 1 and 3, 1 and 4, 2 and 7, whatever we wanted to, and therefore we conclude that the left side eigenvectors transpose times the right side eigenvectors is 0, or that the left and the right side eigenvectors are orthogonal. Okay? Now, if we collect all the right side eigenvectors in a matrix, well, no, before that, I guess we can say that if the right side eigenvector, if the left side eigenvector j transpose is multiplied times the right side eigenvector j, that of course is not equal to 0, right? It's when these two subindices are different from each other that this is 0. Now we can normalize, because the eigenvectors are normalizable, right? We can normalize, we can multiply by whatever it takes, so that phi j transpose times Cj transpose times phi j is equal to 1. And that is a convenient normalization that we will adopt throughout, beginning right now. Therefore, you can see here that if you collect all the left side eigenvectors in a matrix, right? And all the right, and you call that matrix the same symbol, but let's go like that. And you use this symbol to gather all the right side eigenvectors, phi1, phi2, phi(n). Then this that we have here, and assuming that we have the appropriate normalization, means that this matrix times this matrix is the identity, right? Or, what is the same, that the transpose of the left side eigenvectors is the inverse of the right side eigenvectors, provided that the normalization has been done appropriately. Now, at this point, it's important to recognize one thing. The right side eigenvectors, or the left, it doesn't really matter, can be normalized arbitrarily, right? For example, I can have A times phi j is phi j lambda j, right? And I could decide to normalize that the norm of phi j is 1. That's fine, right? We could do that. But notice that you cannot do, once you say this, you cannot say that the norm of the left side eigenvectors is also 1. And at the same time say that this is true. So once you normalize the right side eigenvectors in a particular way, the normalization of the left is now constrained to be something specific if we want this relation to hold. Okay? And having this relationship holding is very convenient, or which is the same, this one here. All right? So, I believe that we are ready to tackle the question of the sensitivities. Okay. So now, let's assume that let's start again and say that this is our problem. A is a function of our parameter. If A is a function of the parameter, it's clear that the eigenvectors are also a function of the parameter, and that we have something like this, right? This is the eigenvalue problem where A is a function of some parameter, the parameter that we want to jiggle to see what happens. Now, I'm not going to write theta all the time because the notation gets quite cumbersome. So instead, I'm just going to say, let's write A times phi j is equal to phi j lambda j, but we know that we mean in this discussion that they are a function of some parameter. Now we want to take a derivative of the equation, and the chain rule operates in standard fashion. It tells us that the derivative of A times phi j plus A times the derivative of phi j is equal to the derivative of phi j times lambda j plus phi j times the derivative of lambda j. Okay? And we're going to use this equation later on. So in your notes, if you'd like, remember that we're going to call that equation A, which is when we take the derivative. Now, let's pre-multiply equation A by the transpose of the left side eigenvector j. And so we have Cj transpose times A prime times phi j plus Cj transpose times A times phi j prime is equal to Cj transpose times phi j prime times lambda j plus Cj transpose times phi j times lambda j prime. Okay? That is our equation at this point. And now, let's see, what do we want to do to simplify? Well, okay, we can do a few things. We can say right away